All right, today we are diving into a world that operates on the absolute strangest rules of the universe, all to unlock a whole new frontier of problem solving. We are talking about quantum computing, a technology that honestly promises to reshape pretty much everything, from medicine to finance. So let's get right into what makes this tech so incredibly revolutionary. But first, let me ask you something to kind of set the stage. What if there are challenges out there? I'm talking about things like perfectly simulating a new molecule for a life-saving drug, or creating financial models that just don't break, that are so complex, our computers today would take literally thousands of years to solve them. This isn't science fiction, you know? This is the fundamental limit of what we call classical computing. And believe me, the race to smash past that limit is already a multi-trillion-dollar bet on the future. This number you're looking at, $1.3 trillion, that's the estimated size of the quantum computing industry by 2035. That's just how much value the world's top companies and researchers believe is locked away, just waiting to be unleashed by this new kind of technology.
So how does it actually work? Well, the magic behind all this massive potential, it starts with a single, tiny, and, let's be honest, a very weird building block. It is time to meet the mighty qubit.
Okay, so to really get the difference, just think about your laptop or your phone. They all run on classical bits, and each bit is just a simple switch. It's either on, which is a 1, or it's off, a 0. It's binary, simple as that. A quantum bit, or qubit, on the other hand, well, it can be a 0, it can be a 1, or, and this is thanks to a bizarre quantum phenomenon, it can be a combination of both at the exact same time.
And here's where your brain might start to hurt, just a little. See, this ability to exist in multiple states at once leads to a straight-up explosion of computational power. While 100 of those classical bits can only represent one 100-digit number at a time, 100 qubits can represent every single 100-digit binary number, all at once. The scale of that is it's astronomical.
Now, this incredible power isn't just random chaos. It's all governed by a set of bizarre, totally counterintuitive rules straight from the quantum world. So let's explore the 4 key principles that make this whole thing possible.
First up is superposition, which we kind of just touched on. The best way to think about it is like a spinning coin. You know, while it's in the air, it's not really heads and it's not really tails. It's sort of a blend of both possibilities. That's superposition. A qubit holds on to this blend of 0 and 1 right up until you measure it, and at that moment, it lands on a definite state. Next, we have entanglement. Okay, this is where it gets really weird. You can link 2 qubits together so that their fates are completely intertwined. If you measure 1 and find out it's a 0, you instantly, and I mean instantly, know its entangled partner is a 1, even if it's miles and miles away. It's this deep connection that allows for some unbelievably complex information processing.
So, if superposition creates all these possibilities at once, how in the world do you find the one right answer? That's where interference comes in. See, in the quantum realm, each of those possibilities acts kind of like a wave. A quantum algorithm very cleverly controls these waves, making the waves for the right answers grow stronger and stronger, while the waves for all the wrong answers, they just cancel each other out.
And that's exactly why you'll hear people say that interference is the true engine of quantum computing. It's not about checking every single answer one by one. It's about using physics to make the correct solution just naturally emerge from this giant sea of possibilities. It's the active part of the machine that finds that needle in the haystack.
But, you know, there's a villain in our story: decoherence. Qubits are unbelievably fragile. The tiniest vibration, the slightest change in temperature, any noise at all from the outside world can make them lose their quantum state and just collapse. And that creates errors. Fighting decoherence is, without a doubt, one of the biggest challenges for quantum engineers today. Okay, so we've got these mind-bending rules, but what are they actually good for? Let's take a look at how these strange principles translate into real-world, practical payoffs.
Let's use an analogy. Imagine a massive, unbelievably complex maze. A classical computer, it would solve it using brute force. It would try one path, hit a dead end, backtrack, and then try the next one. It would have to literally walk down every single possible route one by one until it finally stumbled upon the exit.
A quantum computer, on the other hand, approaches that maze completely differently. It doesn't test paths one by one, no. Instead, by using superposition and interference, it gets this kind of bird's-eye view, evaluating the probabilities of all the paths at once, to efficiently find the exit. It's just a fundamentally faster way to navigate all that complexity.
And that brand new approach could revolutionize entire industries. I mean, think about pharmaceuticals, simulating molecules to design new drugs faster than we ever thought possible. Or chemistry, discovering entirely new materials. Even machine learning could find deep patterns in data that are just invisible to classical AI right now. It could even break the very encryption that secures our entire digital world today. The potential impact is, well, it's enormous.
Now, this all sounds incredible, but let's be real, we're not quite there yet. The journey from the machines we have today to these world-changing quantum computers, it's a marathon, not a sprint. So let's take a look at the road ahead.
The challenges are definitely significant. Engineers have to build processors with more and more stable qubits. They have to develop these incredibly sophisticated error correction systems to constantly fight off that decoherence we talked about. And oh yeah, they need to shrink the hardware, which right now can be the size of a car and needs to be kept at temperatures colder than deep space.
But, and this is a big but, progress is moving incredibly fast. This roadmap from IBM, for example, it shows a really clear, aggressive path forward. Just last year, they achieved what's called quantum utility, meaning their machines can now solve certain problems that are beyond brute force classical simulation. And they're aiming for even bigger milestones in the coming decade.
And this brings us to a really key distinction, the difference between quantum utility and quantum advantage. So, quantum utility is where we are now. It means we have a useful scientific tool. The ultimate goal, though, is quantum advantage, the point where a quantum computer provides a better, faster, or cheaper solution than any classical computer on Earth for a practical problem. And that, right there, brings us to the most exciting question of all. We have officially moved from just theory to reality. The era of quantum computing has begun. So now that we can actually build these incredible machines, the real question is, what impossible problems, the ones that have held humanity back for decades, should we solve first?